Okay, so molarity is given to us as, usually the symbol is big M, and it equals moles of solute per liter of solution. Okay, this is a very, very important one. We use this a lot. Okay, so they give us a molarity here. So every single time I see the big M, I always write the fraction like this. Moles per liter. So that big M always transforms into moles per liter, and I'm going to write it up and down like this, not like this. If you do it the second way, you're going to get confused about what you're doing, so just don't. Okay, and then the other fact we have here is that there's 600 milliliters of solution needed. So I can't just straight up multiply those because milliliters and liters don't cancel, but I do know how to convert from milliliters to liters, and then the liter would cancel. So you could either do this as two steps. You could do the milliliter to liter thing first and then multiply with molarity, but you need to show it using dimensional analysis either way. Okay, again, that means that the units are on opposite sides, then they get to cancel. I can't flip 600 milliliters over because it's not a fraction, so that's the one that's going to stay as it is. All right, and so if we do this, we get that we need 0.27 moles of KOH. Okay, well, that doesn't quite answer the question. I still need to go to grams. So in order to do that, we need to know how many grams of KOH are in a mole. That's the molar mass, right? And so I look at the periodic table and find out how much potassium weighs. I think it's about 39.1 grams per mole. And oxygen is 16 grams per mole. And hydrogen, of course, is just 1.01 grams per mole. So I add all of these up to get the total weight, and this way I know that there's 56.1 grams per mole of KOH. I want to put grams on top because I want to cancel the moles that are here, so I'm going to leave it just like that. Every time we calculate a molar weight from the periodic table, it's always grams per mole, not just grams. Okay, so the calculator says 15.1 grams, so that's D. Okay, so osmotic pressure and osmosis. This is something you might have heard of before. Sometimes people tell me that they're going to learn chemistry by osmosis, and they think that, maybe if they put the book against their head when they sleep, they'll just absorb it. Sadly, that doesn't work. At least I've never been able to make it work. If you figure that out, let me know. I'll pass it on. But when people say that, what they're actually talking about is a phenomenon that happens naturally, where this is a container that's shaped like a U, so we call it a U-tube. That was around way before the internet site. But this U-tube is filled on one side with just pure water, on the left, just water. And then on the right is a solution with water and something else. Anything, it doesn't matter what it is. Salt, sugar, whatever. And we have a semi-permeable membrane in the middle. That means, semi-permeable means that some things get through if they're very small, but most things are, stuck. So water is very small, and it's able to cross that barrier. And what happens sort of naturally, the process of osmosis, is when you have a pure solvent on one side and a solution on the other, the water will travel across this membrane without you doing anything, to try and make the concentration the same on both sides of the barrier, of the membrane. Now that's almost impossible, but it still does it. And when it does, since some of the water molecules are going from the left side to the right, that means our water level would go down on the left, and it would increase on the right. And so this solution is less concentrated than it was. That can only go on for so long because gravity is pushing this back down, so it can't happen forever. We can quantify how strong an osmotic reaction is, an osmotic process. It's not really a reaction. But we can quantify this by just putting some pressure on the right-hand side to push the water molecules back to the left until they're even again. The amount of pressure needed is called osmotic pressure, which is got the symbol of capital Pi. These are measured in the same units as any other pressure, the same thing we saw before, things like torr and atmospheres and all of that. So osmotic pressure is measured in the same way that any other pressure is, but it's not talking about a gas, it's actually talking about how hard you have to push to keep water from trying to come to the more concentrated solution. Okay, so this is a diagram showing us what happens if you have a cell. Cells are surrounded by membranes, semi-permeable membranes. That's important because you need to exchange with the environment in order for a cell to be alive. So if we have a high concentration outside of the cell, we call this the extracellular fluid. Extracellular fluid, so outside the cell. If the ECF is highly concentrated, really, really salty, then what happens is all the water that's inside of here leaves. It's trying to dilute the salt. And when that happens, the cell shrinks. That's called crenation, because these look like crenellations on a castle, the little arrow holes like that. That's a crenellation. So that's kind of what it looks like, so they call it crenation. On the other hand, if we have a really low extracellular fluid concentration, then the extra water outside the cell is going to rush in. Both of these situations are really bad, okay? So in A here, we have an isotonic situation for a blood cell. This is an actual picture of a blood cell that's normal. And the oxygens sit right in here, like this. There's two oxygens. So here's your oxygens. There's some iron in the center there where the hemoglobin proteins are, and they hold oxygen. And it's the perfect size, the perfect shape. This little dip in the middle of the blood cell is perfect for holding oxygen. If that dip isn't there, oxygen doesn't get carried. The shape of the cell depends on whether the extracellular fluid is isotonic or not. If it is isotonic, that means that the same amount of water is going in and out. So you're getting an equal exchange back and forth. The concentrations inside the cell are equal to the concentration outside, and everybody's happy. So that's normal blood. That's what it looks like. A hypertonic happens when the ECF is too high. Okay, so that's an example like B. You have too much salt outside of the cell, and so all the water is leaving the cell, and that makes the crenations that we saw on the last picture, the animation on the last slide. And finally, the last one is hypotonic. That is figure C. Hypotonic happens when the concentration outside the cell is very low, and suddenly everything has to rush in. All right, so that gets us to part 2 of the lecture. You can review this information here about how do we dissolve things. Make sure you understand how to use the periodic table to help you organize solubility, especially comparing ionic compounds, and also using the concentration units that we went over. All right, so here's some more practice with molarity, because this one, like I said, this one's important. We're going to calculate a solution made by dissolving 9.35 grams of KCl to make a total 250 milliliters of solution. So 9.35 grams. Now molarity is moles per liter. So I've got to do some conversions. So 9.35 grams of KCl. I want to get it to moles, so I got to cancel grams. And so this is from the periodic table. It's grams per mole. All right, and so if we go on the periodic table and add up K and Cl, we'll get 74.55 grams. The grams are going to cancel, and so that means what I put in my calculator is 9.35 divided by 74.55, and this gives us the moles of solute. To get to the bottom here, the liters of solution, we're going to convert that as well from milliliters to liters. So I want to get to liters, and I know that there's 1,000 millis in a liter. So I divide by 1,000. I am not going to get rid of these zeros because they are significant digits. There's a decimal there, so I got to keep them. This one's not significant, so it doesn't matter. But I got to keep the last 2 zeros because there was a decimal in my original number. I also kept the correct number of sig figs here because we had 3 in the original measurement. So molarity is moles per liter. And so our calculator says that is 0.5 moles per liter, or that's an L. Or you can write big M. Okay, so that's another example of a molarity calculation. Now, these come in handy when we're trying to do stoichiometry, because molarity is really just a conversion factor between moles and liters. Sometimes I want to go from moles to liters, and sometimes I want to go back the other way. But molarity can be flipped because it's a fraction. Just like if I have liters and I want to get to milliliters, I can use this same relationship. I just flip it over. So, so here, if I have 0.175 moles per liter, right? I see the big M and I transform it. Are needed to precipitate 2.5 grams of Ki. Okay, so first off, I'm going to start actually with the Ki because that's where we're trying to get to. So if I have 2.5 grams of Ki, I want to know how many moles that is so that I can kind of go backwards and figure out how many moles of mercury I need. So again, we're going to go moles on top. And iodine's pretty heavy, so the molar mass of this guy is pretty big. But it's 166 grams for every mole. And I put grams on the bottom so that I can cancel that. This is grams of Ki, right? Yeah. Okay. So that gets me 0.0151 moles of Ki. Okay, so that's the first step. Now I've got it in moles. Once I have it in moles, I remember that I can use the molar ratio, which is just, the coefficients of this reaction, in order to convert from 2 Ki's, so the 2 comes from the reaction, to one of the products that I'm looking for. Well, reactants in this case. So effectively, I'm just dividing by 2. And so this tells me that I need to get this many moles of the HgNO3 in order to precipitate that given amount of substance. All right. So what this means is I'm gonna actually come up here, kind of going backwards a little bit, but if I need 0.0753 moles, I'm going to use molarity because I don't have grams. I don't need that. It's not a solid. I've got moles and molarity. So what I'm going to do is realize that big M means that moles per liter. So I put 0.175 moles on the bottom and 1 liter on the top. So that means I can cancel moles. So we enter 0.00753 divided by 0.175, and we get the final answer in liters is 0.0430 liters. Okay, so this is the only thing that's new here, using molarity as a conversion factor. This is a very important skill, so make sure you practice it. There's lots of problems in the textbook and practice test, and we did a lot of this kind of work in 111 too.